Okay, so today we're going to look at section 10.1, points, lines, and planes. So we'll look at some basic geometry first here. And we'll start off talking about points and lines. Define a point as that which has no part. Later expanded to an indivisible location with no width, length, or breadth. Then Euclid came up with some 5 postulates, and the first 2 of them are: a straight line segment can be drawn joining any 2 points, and any straight line segment can be extended indefinitely in a straight line. So let's look at definitions and how they're symbolized in an example. So we start out with a point, which is just a dot, and they're defined with capital letters like point A. Then we have a line segment from point A to B. Note the little line over the AB. A ray from point A in the direction of B. Note there's a little arrow there pointing in this direction from A to B. Likewise, we have a ray from point B to A. The arrow is pointing this direction. And then the line includes the points A and B and goes off indefinitely in both directions. And again, this is symbolized by arrows going in both directions. Then we have what's called a half line from but not including point A and in the direction of B. As you see, we have the open dot here to signify that point A is not included. And here on the side of the A, it's an open dot as well. And then we have a half line from, but not including point B to point A, which is the same thing, except in the other direction. So, for the following exercises, use a line. We want to draw the ray B to D. And we start here with B, we're going to D, and it's a ray. So it continues on. Here we have a line segment from A to B. Color in our points. There we are. Simple line segment. Now I have a ray starting at A and going to B. Now this is where you have to be careful. Note the arrow, even though it's pointing this way, on our number line, we're actually going this way because we're going starting at A and going to B. And here we have the line A to D, so we include point A, we include point D, and we extend in both directions. So here we have a street map. Find 2 ways you could stop at the dry cleaners and the grocery store after school on your way home. So we could go where we want to go. We want to go dry cleaners and grocery store. So I want to go here and here. And then home. Here. So I'm starting here. I could go this way. Go by the grocery store. Go down. Go by cleaners and go home. It's a different color. How else could we do this? But we could go like this and here and then down here, 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 or even this way. Next concept we have is parallel lines, the lines that lie in the same plane and move in the same direction, but never intersect. To indicate that the line L1 and L2 are parallel, we often use this symbol here. The distance s between parallel lines remains constant as the lines extend indefinitely in both directions. So again, parallel lines. Note the distance is the same. It would be the same here as well. Perpendicular lines, two lines that intersect at a 90-degree angle, are perpendicular lines and are symbolized using this symbol here. Looks like an upside down capital T. If L1 and L2 are perpendicular, we write L1 perpendicular to L2. When two lines form a right angle, or 90-degree angle, we symbolize it with a little square, which we have right here. So let's find the sets of parallel and perpendicular lines. So let's look at parallel. Parallel. Well, it looks like this line here and this line here. So we could list it either way. We'll say RS and UV. Those two lines are parallel. What about perpendicular? Well, I guess two lines are perpendicular. We have UV and XY are perpendicular. And also these two, which is RS and XY again, which makes sense. Since RS and UV are perpendicular, if UV is perpendicular to XY, RS will be perpendicular as well. A plane, as defined by Euclid, to identify a plane by three non-collinear points. That means points not on the same line. Think of a piece of paper, but one that has infinite length and infinite width and no thickness. Infinitely. Sometimes a plane is in the figure below, plane P contains points A and B, which are on the same line, and point C, which is not on that line. By definition, P is a plane, and we move laterally in any direction on a plane. So here we go. It's plane P. Right? We have two points, so they're on the line, and the third point is a straight figure here. Okay, so summarizing, 3 points, including at least one non-collinear point, determine a plane. A line and a point not on the line determine the plane. Same thing, right? 2 points define a line. And the intersection of two distinct planes is a straight line. Okay, so let's refer to this figure here. And what we want to know, yeah. So here's point A, at -5, -2. Point B at 4, C 3, -6, D 5 and -2, and E is 3 and 2, and F and 5. Describe the line that includes point A and point B. Ah, A, B. Describe the line from E to F. Or is it wanting the whole thing? Because that would be line A, B, F. The line from E to point F. Yeah, that's got to be it. That is ray. And the ray starting at E and going to F. CD, that is line segment CD. Does this figure represent a plane? Yes, because we have 2 points on a point that's not. So yes, it is a plane. Okay. Intersecting plane. Well, we have this plane here, represented by technically 4 points. It's way too, we'll label it plane A. And we have this plane here, and we could label that plane B, and they're intersecting, and you can see the line of intersection. Likewise, we could have this plane here and A, and again, a line in common. And that finishes up section 10.1.